Okay, so welcome to my first HLIB Unit 20 video. So in this one, we're going to be doing, I'm just going to draw it up here first. We're going to be doing Unit 20, which is an HL only topic. And it's basically organic chemistry and some reaction mechanisms chemistry. So what we're going to be doing in this video, we're going to be going over my slides a little bit and going over a few different reactions basically on the screen right here. So basically, let's begin. So important things to know for this unit are the difference between homolytic versus heterolytic fission. So what the difference here is that homolytic fission, it involves a bond breaking clearly in two. So homolytic fission, this is basically just to start you off in this unit. If you remember back from your unit 10, we talked about alkanes, right? And we said that alkanes are rather unreactive, except for our reactions were burning. We can crack longer chain alkanes, cracking, or we can halogenate them, halogenation. So halogenation reaction is the one that we're going to be covering here for homolytic fission. I'm just going to erase this for now, and then we're going to do that a little bit down at the bottom. So basically what occurs, right, we got homolytic fission. We've got chlorine gas. We've got Cl2. We've got chlorine gas. So in our halogenation reactions, right, it was a free radical substitution reaction. So what's actually occurring is that we take chlorine and we hit chlorine with UV light. And this UV light is proportional to the bond energy holding this chlorine together, to that sigma bond energy holding the chlorine together. So when you hit it with UV light, what you end up causing is you cause two chlorine free radicals to form. And these two chlorine free radicals are very, very reactive. So since they're reactive, they can force an alkane to be reactive. And this is what we call homolytic fission. So how to draw a homolytic fission is you show the chlorine atom or the chlorine molecule, and in order to show it, the important thing to draw here is that you do fishhook arrows. Is you show from the bond up a fishhook. So right, it looks like a hook instead of like a double-sided arrow. So you draw a fishhook onto him, and then you form two chlorine free radicals. So an example of a reaction involving homolytic fission, if you read your textbook, or I'll provide it right here. Of course, we got C2H6. Hopefully you know what this is. Meth F, and it's CnH2n plus 2 is the rule to figure out if it's an alkene, or alkyne. So C2, H, 2 times 2 is 4 plus 2 is 6, which means that it's an alkane. So this one is meth ethane. So we've got ethane here in gas phase reacting with chlorine gas. So we can also write that as Cl2 gas. And what we're going to form is we're going to form C2H5Cl plus HCl. So we're going to form some hydrochloric acid gas, and we're going to form a chloroalkane or chloroethane. So basically from this is the sub-reaction that's happening here. We use UV light, the same thing as before. UV light, I'll do that in blue. So we add UV light to it, and UV light causes the homolytic fission of chlorine to form chlorine radicals, and those chlorine radicals will attack the alkane and form a chloroalkane. And the reason why we want to form these chloroalkanes It's basically because, right, if we look at just ethane, let's just look at an ethane molecule. So we've got a molecule of ethane right here. And if you guys remember, right, our bond polarity, if we're calculating our bond polarity, it depends on electronegativity differences. So basically, the electronegativity differences, but also symmetry. So at this, right, we can, even if chlorine is more electronegative than hydrogen, chlorine will have a delta negative charge here. Hydrogen will have a delta positive charge here. But then the total charge coming in this way is going to be counterbalanced by the charges this way. So we're going to have an equal charge on each side of this atom, and that's why this atom turns out to be a non-polar atom. So there's no charge differences with this atom. If you wanted to look at your chemistry data booklet, you can actually calculate the value for this to figure out that it's a polar or non-polar covalent bond. And what you're going to find out is a non-polar covalent, and that all of these basically electronegativity values cancel out based off of symmetry. So basically where to go from here is we get a little bit of a shift, right? Now we've got a chloroalkane, so I'm going to erase this. We've got chlorine here, and chlorine, like you would have seen from one of the first units, chlorine is extremely electronegative. So you know chlorine is going to pull all these electrons, and he's going to get a delta negative charge over here, and this carbon here is going to get a positive charge. This one's going to start donating some of its electrons over here to counterbalance that positive charge. And we call this the inductive effect. Inductive effect. So it's basically however many carbons are bonded to the carbon that's attached to the halogen, they can donate a little bit of their electron density in order to reduce this positive charge. But we've only got one here, right? We've got a primary carbon. So he's only bonded to one carbon, which is bonded to 3 hydrogens. So you see we've got a big electronegativity here and electropositivity here. He's got a positive charge, and of course carbon doesn't like having a positive charge. So what this positive charge allows for, and this is what we're going to see with Sn2 reactions, what this positive charge allows for, just like what you saw with our d orbitals and basically the octahedral and the tetrahedral structures that come from these dative covalent bonds, is we see that same thing happening here. We see, now that he has a net positive charge, we can have what we call a nucleophile. So right, this oxygen has got 3 lone pairs of electrons that he has available to donate to form a dative covalent bond. So he can donate. So these electrophiles, if the hydroxide bond to carbon is stronger than the carbon-chlorine bond, this reaction will occur because every system wants to reduce its potential energy. Remember, we've got our potential energy graphs. And every system wants to reduce this potential energy. It wants to be as stable as possible. So if this bond attached coming to the carbon is going to be more stable than the carbon-chlorine bond, he can come in and attack and kick the chlorine off. So he can force this chlorine to go off. And we're gonna get into this a little bit more right now. So I'm just going to erase the homolytic fission, and maybe quickly we'll do heterolytic fission, just so that it starts to make a little bit of sense. So this is why we add that halogen group, what we've just done. And how we added it is what we covered with the homolytic fission. So what heterolytic fission is heterolytic fission is where a whole lone pair moves to an atom. So if we imagine, like your acid-base unit, right? We had H2O undergoes auto dissociation to H plus and OH negative, and you say, okay, how does that happen, right? We've got aqueous, and water is a liquid. So how that happens is if you draw out the structure of H2O, what ends up occurring is that the oxygen, because he's so electronegative, can pull these electrons off of the hydrogen and force the hydrogen to give them up. So since it pulls off both pairs, what ends up occurring is that we've got hydrogen with no electrons around it, so that's why we call it just a proton. And we've got, sorry, there shouldn't be an arrow there. And we've got the hydroxide, whereas before he had 1, 2, 3, 4 lone electrons, 2 lone pairs. Now he's got 1, 2, 3, 4, 5, 6 lone electrons. So he's got 3 lone pairs now. So he's gained a pair of electrons. So this is what we call, when you gain a pair of electrons, we call this heterolytic fission. So, and the way that we show heterolytic fission, right, you can see that I did it right here. We use a double-sided arrow. So before with homolytic, right, we had the chlorine, chlorine. We showed that 1 electron goes here and 1 electron goes here. Now that we're showing 2 electrons, we use a double-sided arrow. We put the arrow directly across and down. So we call that heterolytic fission. So let's go into this reaction that we've got down here at the bottom. So basically we just need to go over homolytic fission because that's how we basically activate an alkane to be reactive. So now that we've got a reactive alkane, I'm going to introduce what type of reaction this is, what type of reaction we are going in down here. So this reaction occurs with primary carbons. So mainly with primary carbons, which means that the carbon is bonded to another carbon. And this carbon is not bonded to any other carbon atoms. So he is bonded to a carbon. So this will be our, we'll just say we've got a bromoalkane right here. And this carbon, which is our, our key carbon, is bonded to a carbon that's only bonded to hydrogens. Okay? So that's what our primary carbons are. He's only bonded to 1 carbon. Now if he was bonded to 2 carbons over here, if we bonded him to a second carbon right here, CH3, now we've got a secondary carbon, and then we bond to a CH3 here, and we've got ourselves a tertiary. So this carbon bonded to 1 other carbon is a primary, him bonded to 2 other carbons is a secondary, and him bonded to 3 other carbons is a tertiary. So this only occurs for primary carbons. So basically, this carbon that he's bonded to is only bonded to 1 other carbon. And then this carbon further on can be bonded to a CH3. We know we can have a bigger chain, a bigger chain, a bigger chain. So this should be a 2 and this should be a 2. A bigger chain, a bigger chain. We can see that this carbon is still only bonded to 1 other carbon. So that's what a primary means. And why this is important is because, it's this reaction, what we call it is we call it stereospecific. So it only occurs from 1 angle. So if you imagine we were to draw this out, right? If we draw this out in the 3D space, we've got this carbon is coming out, is going back, comes down to a bromine, and then we've got this R chain on the top. We've got whatever this chain is off to the side. It's just a carbon, and it doesn't matter how many chains there are. So basically we see that, in between over here to the right, we've got some space where another molecule, in this case OH negative, can come in the back side and attack. The more big groups we have down here, the less this hydroxide can come in and attack. So it's important to state that this type of reaction only occurs with primary carbons. So basically terminal end of chain carbons. So what we call this reaction is we call it an Sn2 reaction. So this is substitution. This is nucleophilic. and this is involving two species. So it involves both this group, what halogen is bonded to it, as well as this group, what group's coming into attack. So it involves two different species, and it's a one-step reaction. One-step reaction. So in this reaction, I'm just going to erase this down here. In Sn2 reactions, Sn2, so I'm going to write that here, Sn2, it needs to be a primary carbon. Like I said, that carbon is only bonded to one. The carbon that the halogen is bonded to is only bonded to one other carbon. Sorry, I think I said that a little bit wrong earlier today in this video. But this carbon that the halogen is attached to is only attached to one other carbon. So Sn2 occurs primarily with primary halogens. And the way that we draw this out is let's take an example. I'm going to draw it down here. And let's say we've got a hydroxide group. Hydroxide group coming to attack a bromoalkane. So we've got carbon. Let's just try to draw this to be so that you can kind of see the way it's going to go. Hydrogen here, hydrogen coming out of the screen right here, and that R group going into the board right here, and we've got bromine attached right here. So what you're going to see right here, right, since this is this is an Sn2 reaction. What occurs in Sn2 reactions is there's an intermediate between this being formed. So in Sn2 reaction, we're going to go over what dictates whether an Sn2 reaction is going to occur. But what you see is that this carbon, like we said, has a positive charge, and this bromine has a net negative charge because he's a halogen. And this, being negatively charged and having an extra pair of electrons it never had before, is a good nucleophile. So he's ready to give away his electrons. So he can come in, donate. So he's donating a pair of electrons. So we need a double-sided arrow, and then it's going to kick off this bromine. Right? We can't have a formal charge that's too high on the central carbon. So he's going to come in and kick off the bromine. He wants to give his electrons to the nucleus more than bromine wants to stay bonded to the nucleus, because the bond between this hydroxide group is going to be stronger than the bond between the carbon and bromine group. So we always need to draw the intermediate here. And how to draw the intermediate is square brackets. You draw the carbon main groups as if they're trigonoplanar now. So we draw an H up here, an R going in, and an H coming out. We say that the bond isn't fully formed yet, so we draw a dotted line between the bromine and between the hydroxide. And this has a net negative charge, right? We had a negative charge before, no charge here, so the charge balance, we need to have a negative charge here. So this is what we call a reaction intermediate. And this is our rate determining step. So it's how much this bromine wants to leave versus how much this hydroxide wants to come in and attack the central carbon. So that's our intermediate step. And then the final step at the bottom is we've got the main carbon. The hydroxide is now bonded to the left. And we see that the center has flipped now. We've got an H going to the right, an R going into the screen to the right, and an H coming out. So we've changed the stereocenter. We've inverted it. It's called an inversion. It's a stereocentric inversion, plus Br minus comes out of it. So this is what an Sn2 reaction is. It's basically a reaction where the nucleophile comes in from the backside, attacks the positive carbon to form a more stable bond, and kicks the halogen off. So that's why these reactions are useful, right? We use the homolytic fission in order to form the chlorine radicals. the chlorine radicals can halogenate an alkane, and then from that halogenation, right, we added an hydroxide right here. We've already formed an alcohol from an alkane in 2 steps. So we've gone through a stepwise procedure in order to form it. But the important things to take away from this is that Sn2 occurs with primary carbons. It depends on both the leaving group right here, the bromine, and the attacking group. So if we were to write out the rate for this reaction, it's the rate constant times the halogenoalkane, the concentration, times the concentration of the nucleophile. And that's just, and we say that if it's dependent on 2 different things, it is bimolecular. It depends on 2 different molecules coming together. And we need to remember that it's stereospecific. So stereospecific, which means that always what happens in Sn2 reactions, every single time you see an Sn2 reaction, the nucleophile attacks from the open space on the back side of the halogen. So the halogen's coming right out. You know, if we drew that tetrahedral structure, there's our central. We've got one going into the board, one coming out of the board, and at the bottom. So it always comes in from this gap between these 3. We have, you know, our nucleophile always comes in from the bottom side, flips these over to the top side, and kicks this guy off completely. So it's a bimolecular reaction. Okay, so aside from that, that should be all we have to cover, hopefully, for Sn2s. We're going to cover, you know, what can affect this in the next video. You know, this affects it. How strong the bond is between the carbon and the bromine dictates how good or how much it wants to leave. And also the strength of the bond that this forms in here dictates how much it can kick this leaving group off. So okay, hopefully this made some good sense. If not, message me in Google Classroom like usual.